This is a very simple example. We want to find the current in this circuit. So you have a battery with an EMF of 6 volts, another battery with an EMF of 12 volts, resistance R2, resistance R1. Now, we want to find the current. We're going to put the current in a random direction. We don't want to think what the direction of the current should be from the beginning. If it turns out in the end that the direction was wrong, you'll know it very easily because there'll be a minus sign in the result. So don't worry in circuits in general trying to find the correct direction of current. Now we know that this battery is more stronger than this one, so the current should be in this direction. So this choice is actually wrong, but it doesn't matter. You don't have to waste time thinking about this. Just put it in any direction. So let's put the current going down here. That means it goes around the loop like this. And let's see how we can get the current in a very, very systematic way. We can get VB minus VA, which is what? Which is 6 volts. It's epsilon 1 plus epsilon 1. And then we'll get VC minus VB, which is what? The current goes, based on this assumption for the direction of current, we're going to assume that it's correct. That means the current should be going from high potential to low. That means if we get VC minus VB, then it should be a negative number. So it should be minus I times R1. Now we'll get VD minus VC, and you notice we're going in one particular direction. We're going clockwise. So VD minus VC, what's that equal to? This is the potential at the negative terminal of the battery. This is the plus terminal, so this is at a lower potential than this point. So VD minus VC is minus epsilon 2. And then we go get VA minus VD. VA minus VD, remember the current is going here upwards, so based on this choice of current, this is at a higher potential than this point. So if I'm getting VA minus VD, then you'll get a negative number, so it's minus I times R. If you sum all these, you'll get what? You get 0 for the left hand side, and that's exactly why we chose these particular things to get the potential difference between these particular points. We got VB minus VA, then VC minus VB, then VD minus VC, then VA minus VD. We went in a very systematic way around the loop. You have to do that so that when you add all these, you get 0, because the VB will cancel with the minus VB, VC with the minus VC, VD with the minus VD, and VA with the minus VA. So the left hand side, everything you get 0. Then you add everything on the right hand side and you get that. So that's your equation. That's your loop equation. So if you take the loop equation and then get to try and get the current, you'll get that the current is epsilon 1 minus epsilon 2 over the sum of the resistances. Now, because epsilon 1, the value is less than the value of epsilon 2, you get a minus 6 over 18. The minus sign just indicates that you chose the wrong direction of current. So all you would have to do if you want to finalize this problem is just reverse the direction of the current and put the value, the same value, 0.3 amperes. Remember, we can solve the problem in a faster way by doing this method that we discussed before. You can start at A and say, okay, what's the potential at A equal to? The potential at A is equal to the potential at A, but then what can I do if I go around this way? I go from here to here, the potential increases by epsilon 1. And then when I go from here to here, it decreases by I times R1. And then when I go from here to here, it decreases by epsilon 2. And then when I go from here to here, it decreases by I times R2. So the potential at A is the potential at A plus this, minus this, minus this, minus this. You get back to the potential at A. And then you cancel the potential at A, VA cancels with the VA, and you get the equation that the same equation we got before. This is a kind of a quicker way to do it, to make the loop equation in a quick way.